Hey guys, welcome back to Genius Learning. I want to keep taking a look at this problem with the sliding block, but this time we have a different situation. We have that the angle of the incline plane is 24 degrees. We have the mass of the block is 10 kilograms, and the block slides down with a constant speed after slightly being pushed down. So this word constant right here, when you see this in the problem, we need to learn how to take advantage of these type of like secrets inside of the problem. So we'll take a look at that. Before I do that, I want to choose my direction here, because that's always the most important thing. So I want to say that going up perpendicular to the plane is my y direction, and this time I want to choose going downward as my positive x. So this direction, positive x, and then opposite to that is the negative x. Okay, so now that I've chosen that, let's take a look at what they're talking about over here. Okay, so we have our initial position of the block here, okay, and we drop the block right there. So it says that the block slides down with a constant speed after slightly being pushed down. So after it reaches about here, right, the slightly being pushed down part, then it travels with a constant speed. So let's say this is our V initial, just to differentiate this beginning one. Okay, now when it reaches here, this point, it starts traveling with a constant speed all the way to this velocity final here. So we're going to say that this point here is our velocity initial, and then this point here, right when it gets to here, is our velocity final. But during this time, it was traveling at a constant speed. So the change in velocity was 0. Okay, so let's take a look what that means in this graph here. You would have velocity versus time graph. Okay, and we're gonna say that here is our velocity initial, and here is some other velocity. So we're increasing in velocity going this way, and here's our initial velocity, which is this one. Okay, so initially we're here. Let's say we're close to down here, right at 0, and we increase in velocity till initial velocity, until the velocity starts being constant. So we increase our velocity until velocity initial, right? And then from here to here, it's a constant speed. So if you're constant, you're not changing your speed. So there's no change in our velocity. So our velocity goes from here, and let's say it ends up right here to a certain time final, right? So this is time initial, and then this whole length here will be a time final where it finally stops, and this is our V final. Okay, so here, this whole block represents constant speed, right? You can see that the velocity initial stays right there and doesn't change. All right, it increases speed up until it starts going at a constant speed. All right, so this is the area under those curves. All right, so then what we want to write for our notation, let's see, is going to be acceleration average is going to be equal to the limit as the change of t approaches 0 of the change of v over the change of t. So that just means that the change of velocity over the change in time as we approach a 0 time. You have to go all the way to the end and stop. Then we can have the derivative of velocity over the derivative of time, right? So by saying that we have a constant speed, right, we're saying that this is our change in velocity, right? V final minus V initial. And so let's say here at our V initial, let's say for some reason our V initial is at 2 meters per second, right? So we increased all the way to 2 meters per second, and then we remained 2 meters per second, right? A constant speed all the way to V final, where again, we're at 2 meters per second. So here you're gonna see that 2 minus 2 is gonna be 0. So our change in velocity is 0, therefore our acceleration, which is our change in velocity over the change in time, is equal to 0. Okay, so now let's see how we can take advantage of that and use this equation, okay? Just let me point out a small difference here between average acceleration, because it is a little bit confusing. So I'm just gonna give one more small example here. And this graph represents velocity in the x direction and time. Okay, we have a certain velocity initial in the x, and then a velocity final in the x. Okay, so that reaches here and that reaches here. This will be 0.1 and this will be 0.2. Okay, so what we mean is that if I want the velocity here, okay, then the slope, right, there's a tangent line that goes like this right on that point, and that tangent line represents the acceleration of x, okay, which is the derivative of velocity in the x over the derivative of time. So this is what we mean by an instantaneous acceleration. Right there, what's happening. Right there, what's the acceleration. Okay, and then the difference of that and the other thing that we're calculating is gonna be from this point to this point. So here to here. It doesn't matter the path that it actually took. We just want an average from the entire thing, a straight line. And so this average, right, can be represented as the change in velocity in the x, which is velocity final in the x minus velocity initial in the x. That's this right here. Okay, and so acceleration average is the change in velocity in the x over the change in velocity, the change in time. Okay, so this is the difference. And for this problem, because they said constant speed, this is 0. So our average acceleration is going to be 0. Okay, so now let's use that and see how we can take advantage of that. Okay, so we have Newton's second law. We got the force net equal to ma. Right, so we're going to do the force in the x direction. So the net force in the x direction. Let's establish here a free body diagram onto the mass. Okay, so down goes gravity vector. Okay, we got the normal force, which is perpendicular to the box, and we're going to draw a dashed line going down where we have this triangle, and so we have mg cosine theta. Okay, and I derived this in a previous video, so if you're not familiar with that, go check out the previous video. All right, and then we have the last vector, which goes parallel to this line here. Okay, it goes like that, and that's another 90 degrees, and this is the angle. So this is mg sine theta, right? So going down is going to be mg sine theta. All right, so now which way is friction? So we're moving downward. Friction is opposing our motion, right? Friction always wants to slow us down. So in order to slow us down, the friction component has to be opposing the motion. Okay, so now force in the x is going to be, I labeled going down positive, so we're going to have mg sine theta minus friction, which is going upward, is equal to m and acceleration in the x, because this is our x-axis, okay? And we're gonna leave a little space, and then now we have the sum of forces in the y, right? The net forces in the y. So this box here does not want to go up and down on the plane. Oof. And so because of that, we have n minus mg cosine, which is equal to 0. Okay, so in other words, if we rearrange this, our normal is equal to mg cosine theta. And so this is here is telling us that this box will slide down and it won't jump up and down as it slides. Okay, so we're gonna need this. And we also need to know that friction is equal to mu, which is the coefficient of friction, and times the normal. The normal is mg cosine, so our friction is mu mg cosine theta. Okay, we use this into our force in the x direction, right? And so we're gonna get mg sine theta minus mu mg cosine theta, and that's all equal to m acceleration in the x. Okay, so the mass are all the same because we're only dealing with one object here. Okay, and then also remember that our acceleration in the x is 0 because we're at a constant speed, so there's no change in our velocity, and so this side here is going to be 0. And now we're able to solve for our coefficient of friction. So if we put cosine on the other side, we got g sine theta equals, we'll put this on the other side, which is mu g cosine theta. Okay, we're going to divide by g cosine. So if we divide by g cosine, we're going to have g cosine here, g cosine here. So the g's cancel out, this cancels out, and we're left with tangent of theta equals mu. Okay? All right, so now we have the angle, right? Because we're given that from the beginning, and so we can calculate our coefficient of friction. So let's take a look. We have here tangent of 24 degrees is equal to mu, and so we got 0.445, which is equal to mu. Okay, and your coefficient of friction should always be less than 1, so that'll be a clue to know if you're doing it right or wrong. I'm gonna write it up here. I'm not sure if I got this in the video here. So tangent of 24 degrees, which is what we found here, is equal to mu, and tangent of 24 degrees is 0.445, so that's our coefficient of friction. Okay, and so this number should always be less than 1. Right, and so that's how you do that.